All right, lesson 4, tables, equations, and graphs of functions. So we've been looking at functions the last few lessons, and today we're going to connect the equations to the graphs of functions. So we're going to be looking at equations a little bit still, but focusing mostly on the graphs and how they all kind of connect, right? So our first activity is a notice and a wonder. So take a minute, push pause, and write down something you notice about the graph and something that you wonder about the graph. So push pause and do that. Okay, so a few things that you maybe noticed. The graph looks like a sideways V, or maybe you described how the graph goes one way and then doubles back on itself. The graph is made up of pieces that kind of look straight, but they're not quite straight. Or you could even focus on the X and Y coordinate information. Like it looks like the distance goes from 0 to 200. Maybe the time goes from 0 to 72 seconds. Um, the vertical axis tells us the time in seconds. The horizontal tells us the distance. So, all different kinds of things that you could have noticed. And of course, the wonders, you could take the notice and turn it into a wonder. Or maybe you wonder who the graph is about. Or is this person running or walking? Um, is this about one person or is it more than one people? If it is a person, why does the graph go one way and then come back the other? What would the title of the graph be? So, all different kinds of things. You need to make sure that you have one of them written down. Right. Next page. 4.2 Equations and Graphs of Functions. So, the graphs of three functions are shown. Okay, we have A, B, and C. Number 1 says match each of the equations to one of the graphs. Okay, so we're going to have to match each of these situations with one of those graphs. All right, so let's take a look at A. A says distance equals 60t, where d is the distance in miles that you would travel in t hours if you drove 60 miles per hour. So d is the distance, t is the hours. So we've got to try to figure out how to match on this graph. Okay, well, one kind of place to start, because we can't tell, like, is the t on the horizontal or is t the vertical? Where does distance go? So we can kind of do a little bit of like a guess and check kind of thing, just to see if it can kind of help us figure out. Um, so if we think about this is distance as we travel with hours. So as our hours get bigger, our distance also gets bigger, right? So if t equaled 1, that's 1 hour, right? If t equals 1 and that's 1 hour, my distance would equal 60 times 1 instead of 60 times t, right? So that means my distance would equal 60. So we can kind of look on this graph. Is there, which of these has a point where when the t is 1, the d could be 60? Well, if I look here, if this was my t, that definitely right here would not be 60. If this was my 1, that looks like it could possibly be 60. Now, 1 would be really tiny down here, and could maybe that could be, no, that's 50. So C is probably out. Let's look at another option. What if T was 2? That's 2 hours, right? So then it would be distance equals 60 times 2. So my distance would be 120. So which of these graphs shows me a point where a T could be 2 and the D could be 6 or 120? Well, here, if it's 2, that's definitely not 120. There's 2, that looks like it could be 120. Here, if 2 was this little one here, definitely not 120. So it looks like B is our match for this. This would be distance equals 60t. A couple other things you could think about for this would be, I know that as my time increases, my distance increases. So I've got to have one of these graphs where it looks like it's increasing, right? This looks like a decrease. So as this increases, this number decreases, right? The other thing that we can remember is that from our previous lessons, we knew that we had the input, then the rule or the equation, and then the output, right? And our equation included the input. And we also kind of started talking about how the input was our independent variable, output is the dependent variable. Something else that you'll find happening with graphs is that the input is our x value and the output is our y value. So on our graphs, you'll see that our x axis are the inputs. And our y coordinate or our y axis is the output. Okay, so you can even label that. So if we look at B, if our function rule ends up equaling the output or the y, this number that is on the other side of the equal sign is our output or our y every time. So this would be distance and this would be time. The input is included with the formula or the rule. Okay, so let's look at that with B. So in B, our input is included in the rule here. And our output is all by itself after the equal sign. So we have Q equals 50 minus 0.4D, where Q is the number of quarters, D is the number of dimes. So D is inside of our equation part our rule, so that's going to be the input. Q is what we result with, so that's our output. So I know that when I look at the graph, I'm going to be looking for the bottom or the horizontal axis to be the input, and this will be the output or my quarters. Okay, so we have a pile of coins worth $12.50. So this should be kind of familiar. It was our quarter and dime activity. So if we think about this, Q is the number of quarters, D is the number of dimes, and they total $12.50. So if we kind of think of a number that we could have for D, so if D is the number of dimes, so if I have one dime, right, then I'm going to take my equation, 50 minus 0.4 times 1, which becomes 50 minus 0.4, which equals 49.6. So if we look at our graphs, which one could possibly have D equaling 1, and remember D is our input, and 49.6 equaling our output or Q? Well, if D is 1 here, that's definitely not 49.6. We come over here, my 1 would be tiny, tiny down here, but if I go up, that could possibly be 49.6. This definitely is not. This could possibly be. So I'm going to say that this is our answer. And if you think about it, with my input, this would be dimes, and the output would be quarters. And the more dimes that I have, the less quarters I would have, if you think about it. So as my dimes increase, that means I have less quarters that would total up the $12.50. So that's C, which means that C matches with A. But we're going to go ahead and look at it anyway. So A equals pi r squared, where A is the area in square centimeters of the circle with radius r. So A is the area, radius is r. A is by itself after the equal sign, so that's our output. Radius is inside the rule, so that's our input. So if I say that my radius is 1, that would be pi times 1 squared, right? That's going to equal pi, or 3.14. That would be the area. So if r is 1, then A is 3.14. If r is 1, that looks like it could be about 3.14. Okay. Number 2, label each of the axes with the independent and dependent variables and the quantities they represent. So we've already started that. We just need to write a little bit more. So basically what they want us to do is go to the x and y axis and say radius and area. Time says the quantities they represent. So if you look at part A here, it's T is hours. So time in hours. Distance in miles. So we would say distance in miles. Here's dimes and quarters. So we've pretty much already done number 2. Number 3, what is the output when the input is 1? Now we've done that for each of them. We actually did the math. What does it tell us about the situation? Label the corresponding point on the graph. Okay, so we've already done that work. And we even kind of have some points on the graph. So if we look at A, when time was 1, the hour was 60. So we go over 1, and we're going to go up to 60. And we're going to plot the point. What does this tell us? This tells us that when we have 1 hour, we went 60 miles. Okay, so we're going to answer 3 kind of below here. So for A, 160 means we went 60 miles in 1 hour. Okay, now part B, here in purple, when our output or our input, the dimes was 1, the output was 49.6. And if we looked here, input was 1, 49.6. So do your best to kind of mark that spot. And what that means is when I had 1 dime, I had 49.6 quarters, which actually is impossible, but for the purpose of the graph, we're just going to kind of go with it. Okay, so B, our point was 1 and 49.6. If you have 1 dime, you have 49.6 quarters. And the last part, C, the input was R equals 1, the output was 3.14. And that's what we plotted right here. What that means, oops, if we look here, if my radius is 1, my area is 3.14. That's all this means. The x is radius, the y is area. So if the radius is 1, the area is 3.14. Okay, take a look at the next activity. Running around a track. Kieran was running around the track. The graph shows the time t he took to run various distances. D. The table shows his time in seconds after every 3 meters. Okay, so our graph shows time t to run various distances d. Okay, so here's our time and here's our distance. So let's look. We also have a chart. Okay, so this is his distance and this is his time. And if you look, our distance is on the x-axis and our time is on the y-axis. Okay, so keep that in mind as we look at our table. Part A, how long did it take Kieran to run 6 meters? Okay, so if he runs 6 meters, that's a distance. How long, that's a time. We know that it's 6 meters, we don't know how long. So we can use the graph or the table. If I look at the graph, I'm looking for distance 6 meters. And I can go up and I can see here that at 6 meters, it was 2 seconds. If I look at the table, 6 meters, here's my distance, 6 meters, 2 seconds. Okay, so you can use either the graph or the table. So how long did it take him to run 6 meters? 2 seconds. Part B. How far had he gone after 6 seconds? Okay, so now we're looking for distance. 6 seconds. So now we know that the time is 6 seconds. How far did he go? So you could look either at your graph at the time for 6 seconds, or you can look at the table when the time is 6 seconds. So figure out how far did he go in 6 seconds. So I marked the table here is 6 seconds, and the graph here is 6 seconds. Either way, you will see that it's 18 meters. Okay, I want you to push pause and you're going to finish C, D, and E. And then check back here to see how you did. Okay, C says estimate when he ran. So estimate when. And he ran 19.5 meters. So we need to estimate. So here's 18. That might be 19. That might be 20, right? If I kind of break that up. So 19 and a half would be somewhere around here, which is somewhere between 6 and 7. So I would say this is a way to say approximately. So approximately 6.5 seconds. And if you look at the table, between 18 and 21 would be somewhere in between, could be about 6.5. Probably easier to get that from the graph. Now, part D, estimate how far he ran in 4 seconds. So I have my time. We're going to estimate. Again, probably a little bit easier from the graph. So at 4 seconds, so we can probably kind of mark that this might be around 4. Well, that's definitely not 1.5. It may be closer to, I don't know, 1.2, 1.3. And make sure that you're labeling with the numbers. So as long as you got something that's around 1.2, 1.2, 1.3. And E, is Kieran's time a function of the distance? Okay, so is the time a function of the distance? So what that is asking is time a function of the distance? In general, what we have is the output is a function of the input. So is time a function of the distance? So is time the output and distance the input? That's what we need to figure out. If time is the output and distance is the input, then yes. Does time depend on the distance? And yeah, it does. Okay, so if we look at this, my x is the distance, x is the time, excuse me, x is the distance, t is the time is the output, right? So this is our input and this is our output, right? So time is our output. So if I look back here, output is a function of the input. So we could say yes, because the time depends on the distance. Okay, next page. Priya is running once around the track. The graph shows her time given how far she is from her starting point. Oops. Okay, so now this looks just like the warm-up, right? What is her farthest distance from the starting point? So if we look, our x-axis shows distance from the starting line, and our y shows the time in seconds. So this is the start, right? Distance from the starting line. What's the farthest distance from her starting point? So if she starts here and she gets further away, further away, further away, further away, and then she comes back closer. So this is showing her getting closer to the start. So this right here is farthest away, right? And if we look at our intervals, 100, 125, 150, 175, that would be 200. So part A, her furthest distance would be 200 meters. Part B, how long did it take her to run around the track? So estimate how long it took to run around the track. Okay, well, this is our time, right? She started at 0, and as she went away from the start, that took her a little over 36 seconds. And then this is her coming back. So this right here is going to tell us her total time, right? So we need to estimate. It's not quite 72. If we look, each of our lines is 12. So I don't know, what do you think? If each line is 12, or maybe 74 seconds, 75 seconds. Estimate when she was 100 meters from her starting point. Okay, so if we look at 100 meters, she was 100 meters right here, and she was 100 meters right there. So when was she 100 meters from her starting point? Estimate. Okay, well, this looks like it's about halfway in between. These are each 12, so that would mean the in-betweens would be 6, right? So 6, 12, 18 there. So somewhere about 18 seconds here. And then if we go up here, each of these are 6. So that would be 48 plus 6 is 54. I don't know. Do you think that's around 54, 55? Something like that? So she was 100 meters away at 18 seconds and about 54 seconds. and 54 seconds. Or you could say 55 or 56, depending on your opinion. Part D, estimate how far she was from the starting line after 60 seconds. Okay, so let's go find 60 seconds. So after 60 seconds, she's about 75 meters, right? So D, she's about 75 meters. Okay. And then part E, is Priya's time a function of her distance? So if we remember what we talked about before, the output is a function of the input. So the output depends on the input. So is time a function of the distance? Well, if we look, time is the output, distance is the input. So if we say yes, that means that the time depends on the distance. So I want you to write this question down. Does the time depend on the distance? Now, on the last problem, it did. Okay, if you told me the distance, I could tell you the time. So in this case, if I tell you the distance, could you give me a for sure time? So let's go look. If I give you the distance, could you tell me a specific time? Yes, but you would actually tell me two times. If I told you the distance was 100, you would tell me two different times. So there isn't really a for sure time based on the distance. There are two times based on the distance. That's a problem. If I give you the distance, you should be able to tell me one single time. You can't I can't be it's like that activity where, if I give you the letter A, you tell me some name that starts with A, but we could all have different names. That doesn't Functions don't work that way. You have to be able to give me one specific answer or one estimate. In this case, I can give you two estimates. Because there are two possible answers, the time doesn't depend on the distance. It's not a function. So write not a function. We could get two different times given the same distance. You can't do that and have it be a function. I have to give you one distance and you give me one time. Okay, so to wrap up this lesson, grab your math notebook. You're going to do a little copying of information. So get out your math notebook, push pause and copy this down. So the graph of a function is all of the coordinate pairs x, y, or input, output, plotted on the coordinate plane. Okay, so we take all of the ordered pairs from our function and we plot them. If you haven't got that copy, push pause because we're going to the next part. Okay, here's the next thing I want you to copy down. And when you draw these graphs, just get close to what I drew. Doesn't have to be exact. So pause and get that copied. So the graph of a function will never double back. And that's this kind of thing here where we had Priya, where she ran across the track and then came back. So the graph of a function, you can have a graph that does that, but it will not be a function. So the graph of a function will never double back or have two y values for the same x value. So if we look at the first graph, at any point, all my x's have one specific y that matches. Over here, some of my x's are going to have two different y's. The x here would have a y value here, and it would have a different y value there. That means it's not a function. So if I did this kind of motion and I hit this graph in two spots, that means there are two duplicate y values, and that is not a function. So get that copied, push pause, and when you're done, this is it.